In chicken, the inheritance of a white color is dominant over the inheritance of dark color, and the inheritance of a pea comb is dominant over the inheritance of a single comb. If two chickens, both heterozygous for both traits, are crossed, 111 white with pea comb, 37 white with single comb, 34 dark with pea comb, and 8 dark with single comb are produced, is there a significant difference between the results and the Mendelian ratios? Are the genes linked? So we're going to use a chi-square test to be able to answer these questions. Now the first thing is, let's be able to find out what are the alleles we are going to use. So let me use for white color, since white color is dominant, let me use capital W. And dark color is recessive, so I'm going to use small w. And for P, Pcom is dominant over single com, so let me use capital P to mean Pcom, and then small p to mean single com since it's recessive. Now we are crossing two individuals which are both heterozygous for their traits. That means it's heterozygous white and also heterozygous Pcom. So both have got the same genotype. Now before they can cross over, there will be a sorting of gametes just within the individuals in the process of meiosis. And we know that during meiosis there is also genetic recombination which happens, so there can be some sort of crossing over if the genes are not linked. But if the genes are linked, they might not be crossing over. Okay, so here what we are going to do is we are going to get the gametes for this individual. And for the gametes, this is going to pair up with this. And then again, this same capital W pair up with that to form the gametes. So we are going to have capital W and capital P. That will be the first gamete. And then capital W go also with small p. So there is another gamete. Small w go with capital P also. And then small w go with small p. So these are the gametes which are present in one individual. Now we know that they are both having the same phenotype, therefore even the other one is going to have the same kind of phenotype, genotype in this case. Even the phenotype is the same. Okay, there. And so these are the individuals which are going to cross. Now let's get to perform the cross and see what we are going to get. So these are the genotypes of the offsprings that we are going to produce. Now we should be able to determine first how many offsprings, what is the ratio of the offsprings which are expected to be white with pcom, white with single com, dark with pcom, and also dark with single com. So let's do that. So I'm going to first start with white with pcom. I'm going to use this very section here. So what we are going to be putting is white and pcom, and also white and single com, also dark and pcom, and also dark and single com. So we know that white is dominant and pcom is also dominant. So therefore we need to look for the genotypes where we've got capital W and also capital P. So you can see this one, 2 there, 3, 4, 5, 6, 7, 8, and 9 here. Those are the ones where we've got at least one capital W and at least one capital P. So there are the 9 of them. So we are going to put 9 here. That's a ratio. And let's look for those which are white but with a single comb. And we know that single comb is recessive. So we're going to look for where we've got capital W, but they should be both small p's. But at least even one W. Okay. So capital W and small p's here. and then come to W is small p is there. Another one we can get is here. So we can see those are 3. So I'm going to put 3 here. And then I'm going to look for the dark and the P comb. So dark is supposed to be small w's. P comb we should have at least a capital P. So which one will be those? So it should be small w's, 1, but at least a capital P, 2, and then 3. So they are also in a ratio of, there are also 3 there. And what of dark and single? Dark is recessive. Single is also recessive. That means they should all be small letters. Small w's and also small p's. So you can see we only have this one which has remained. So it's only 1. So these are the ratios that we expect. 9 to 3 to 3 to 1. So this is always the expected ratio when you're talking about dihybrid crosses. Unless if there are some mutations and post-Mendelian genetics. But for Mendel, this is the ratio that we get to expect. So from here, let's look at the numbers. What will be the total for this ratio? So 9 plus 3 plus 3 plus 1, that is going to give us a 16. And what of those which were actually produced? How many are they? These are the ones which are expected. So let me just write here expected. Now these are not really numbers, but they are just ratios. So expect 9 out of 16 to be white and P-comb. We expect 3 out of 16. We also expect 3 out of 16 here, and then we expect 1 out of 16. Now how many did we get? We can see 111 white with P-comb. So I'll put white with P. I'm going to put those are the ones which are produced, or those which are observed. So I've got 111 here, and then 37 white with single comb. We have got 34 dark with P comb, and then we've got 8 dark with single comb. Now what is the total also here? So that is 111 plus 37 plus 34 plus 8. So that is 190. Okay, so that is it. So let us now find the exact ratios which we do expect. These are the ones which were observed. Now what are the ratios which we expect according to the numbers that we have? What are the ratios which we do expect? So firstly, we expect to have 9 out of 16 of the total. Now the total here is actually 190. So we're going to say 9 out of 16 of the total, which is 190. So 9 divided by 16 times 190. So we expect to have 106.9. And we also expect 3 out of 16, but we have got a total of 190 offsprings. So 3 out of 16 times 190, giving us 35.6. Again, we expect 3 out of 16, that is also 35.6. And then we expect 1 out of 16 here. Now 1 out of 16 times 190, that is just 11.9. So these are the numbers which are expected, but these are the ones which are observed. Now we can use the chi-square to see what our answers are going to be. So from the chi-square, the formula is the summation of observed traits minus expected traits squared divided by expected. And therefore this is going to be chi-squared being equal to, first I'll start with this one, observed. We have got 111 minus expected 106.9. we are going to square that and then divide by the expected, which is 106.9. And then plus, we are going to go to the next one, which is observed 37 minus expected 35.6. And then we square that divided by the expected, which is 35.6. Plus, we're going to go to the next, which is observed 34 minus expected 35.6. Square that. Okay, so again we're going to divide by the expected, which is 35.6. This was 8 here. And then the last one, the observed is 8, the expected is 11.9. We'll get to square that and then divide by the expected, which is 11.9. So let's see what we're going to get from here. So if we work out the first on a calculator, 111 minus 106.9 squared, and then divide by 106.9, we're going to get 0.157. And then the next one, we are going to get 0.055. The next, we're going to get 0.072. And the next, we're going to get, that is a 1.278. And when we get to add this, we are going to find 1.56. Now, we have determined this is the calculated chi-square. So what we're going to do is we're going to compare the calculated chi-square and the tabulated chi-square. So let me just now write this value on top there. So chi-square calculated is equal to 1.56. So the other thing that we need to find is chi-square tabulated. What is the chi-square that we're going to find in the table, which is tabulated? Now the first thing to find out here is the number of degrees of freedom which we have here. How do you get to find the number of degrees of freedom? The number of degrees of freedom is given by just the genotype which we have, or the phenotype that we have minus 1. So how many phenotypes do we have here? We have got 4 different phenotypes. We can have either white with picom, white single, dark picom, dark single. So we have got 4 phenotypes. And the number of degrees of freedom is given by n minus 1, which in this case is 4 minus 1. Therefore, we have got 3 degrees of freedom. Now, when we are working on the chi-square, we work at 5% confidence. And 5% confidence, this is the same as 0.05 in decimal places. So we're going to go on the chi-square table and be able to find out what the value is going to give us for 3 degrees of freedom at 5% confidence. So here is the table. We can see this is representing degrees of freedom. This is giving us probability. Okay, or the same code, the point where we're talking about. Okay, the degrees of freedom are here. Now this point here, the 5%, those are the confidence levels. So we want at 5% confidence. So 5% we've said is the same as 0.05. That is the one there. And then we're talking about 3 degrees of freedom, which is here. So what is the value that we are getting? So we're getting 7.8. So that is the tabulated chi-square. 7.8. Now at this point, we are going to compare the calculated chi-square and also the tabulated chi-square. What do we have? So we can see that the one which we've calculated is much smaller than the one which is tabulated. So whenever what you've calculated is smaller than the one which is tabulated, then there is no significant difference. In other words, your values are going to be accepted. They are within the Mendelian predicted ratios. because what you've calculated is below the one which is tabulated. And because the one which is calculated, because there's no significant difference between the Mendelian ratios and our calculated values, then this tells us that this trace which we are talking about, to answer now part B, the trace that we are talking about are not linked, and so they do assort independently. So they are not linked. And we've concluded this because of just this. If this value was bigger than this one, then there would be no independent assortment. That means the genes are not linked. But because the value we've calculated is smaller than the one tabulated, the genes are not linked. Well, thank you so much for watching. Enjoy your day.